Consider a particle confined to a cubical box whose sides have length L. According to quantum mechanics, the wave function of the particle must vanish on the boundaries of the box. This forces the length of the box to be a half-integer multiple of the wavelength, lambda, of the particle in a particular direction. In other words, the only allowed wavelengths of the particle are 2L over n sub x in the x direction, 2L over n sub y in the y direction, and 2L over n sub z in the z direction, where n sub x, n sub y, and n sub z are positive integers. If the particle does not have spin, then each triple of numbers n sub x, n sub y, and n sub z corresponds to one unique state of the particle. If the particle has spin, then there are g sub s spin states for every state characterized by n sub x, n sub y, and n sub z. G sub s equals 2s plus 1 for massive particles with spin s, 2 for massless particles with non-zero spin, and 1 for massless particles with spin 0. We would like to know the density of states for the particle, which is the number of states with momentum between p and p plus dp, where p equals the square root of p sub x squared plus p sub y squared plus p sub z squared. We proceed as follows. We have already shown that the wavelengths of the particle in a given direction must be 2L over an integer. Quantum mechanics tells us that the wavelength of a particle in a particular direction is Planck's constant divided by the component of momentum in that direction. Taking the inverse of both sides and multiplying by Planck's constant shows that the components of momentum must be an integer multiple of h over 2L. If we construct a space whose coordinates are the components of momentum, called momentum space, then we can place yellow dots where the allowed values of momentum are. Each yellow dot is separated from adjacent yellow dots by a distance h over 2L. Thus, each yellow dot effectively takes up a volume h over 2L cubed, or h cubed over 8L cubed. L cubed is just the volume of the box that the particle is in, which we will denote by V. The number of yellow dots per unit volume is just 1 over the volume per dot, or 8V over h cubed. The number of states per unit volume is g sub s times that, since there are g sub s possible spin states for each allowed value of momentum. We want to know how many states have momenta between p and p plus dp. Points with momentum p form a sphere in momentum space with radius p centered on the origin. Similarly, states with momentum p plus dp form a sphere with radius p plus dp centered on the origin. We want to know how many states are between these two spheres, or equivalently, how many states are in a spherical shell of radius p and thickness dp. The volume of a spherical shell of radius p and thickness dp is 4 pi p squared dp. However, we should not count states with negative momenta as separate states, since only the wavelength of the particle determines its state, not the direction it is traveling. Thus, we only care about the states in the 1/8 of the shell that have all positive p sub x, p sub y, and p sub z. The volume of 1/8 of the spherical shell is 1/8 4 pi p squared dp, or a half pi p squared dp. Multiplying the volume of momentum space in the 1/8 spherical shell by the number of states per unit volume gives the number of states with momentum between p and p plus dp. In other words, the density of states.